In this lecture, I will discuss statistical theories related to descriptive statistics. The main objective of this lecture is to delve deeper into descriptive statistics by learning the three main ways to describe data. Before discussing descriptive statistics, we first need to have a shared understanding of what that is. In this course, I'll make references to both descriptive and inferential statistics. The key differences between these two is that descriptive statistics help us understand general trends in the data by providing summary statistics of its shape, average, or the spread of the scores. On the other hand, inferential statistics allows us to take the data analyses a step further, in which we use our sample data to make inferences about the broader population. The two types of inferential analyses that we'll discuss in this course are chi-square and regression. We'll talk more about inferential statistics later on in the course, but for now, let's explore what is meant by descriptive statistics. There are three main ways to describe data. We can discuss its shape, its central tendency, and its variability. I'll discuss each of these in turn. Let's start with shape. By now, you should have heard a lot of discussion around the normal distribution. The normal distribution is something that we rely on a lot in statistics. It was discovered by a Belgian mathematician in 1870. He was collecting information from soldiers in World War I on height, age, IQ scores, chest sizes, and noticed that a consistent theme kept emerging in the frequency of the information, in which there would be a clear peak in the values and a consistent dip in the numbers on either side of the most frequent number. This pattern was referred to as the normal distribution. Since then, we have assumed that all continuous variables are in theory normally distributed. The importance of this assumption is that if all continuous variables are normally distributed, then just by knowing the mean and standard deviation of the distribution, we can predict where most of the scores in the distribution will lie. As shown in this graphic, 34.13% of the scores in a distribution lie within one standard deviation above or below the mean. An additional 13.59% of the scores in a distribution lie within two standard deviations above or below the mean, and an additional 2.28% of the scores lie, that is, virtually all the data, within three standard deviations above or below the mean. The spread of the data in the normal distribution based on the mean and standard deviation is what we rely on when we run inferential statistics and discuss statistical significance. If the shape of the distribution departs from normal, some of these assumptions get violated, and we can reach erroneous conclusions. It is therefore important to be able to recognize the correct shape of the normal distribution and to be aware of the abnormalities that can occur in its shape. The normal distribution has three key features. It's symmetric, meaning that if you cut it down the middle vertically, then the half on the left-hand side would be a mirror image of the half on the right-hand side. It's unimodal, meaning that it has one clear peak in the shape of the distribution. And it's asymptomatic. This means that the distribution approaches zero on the x-axis but never touches it. The first abnormality that can occur in the normal distribution relates to skewness. Skewness refers to the pull of the scores to one side of the distribution that causes the shape to become asymmetric. The shape of the distribution could become asymmetric due to the presence of extreme scores or outliers on the right-hand side of the x-axis. Your distribution would then be described as being positively skewed. You are likely to find positively skewed distributions in a variety of situations, In a classroom, a student who scores much higher than the rest of the class is likely to make the distribution become positively skewed. On the other hand, the presence of extreme scores on the left side of the x-axis could cause your distribution to be negatively skewed. An example of a negatively skewed distribution could also be seen in a classroom setting, where a student scores much lower than the rest of the class. Both positively and negatively skewed distributions are considered to be non-normal. The second type of abnormality in the normal distribution relates to kurtosis. This refers to how peaked or flat the distribution is. If the distribution is too peaked, meaning that there is very little variability in the data, then the distribution is said to be leptokurtic. An example of a context in which you'd find a peak distribution would be in the ages of students in a college freshman class. In this context, there would be very little variability in the ranges of ages. Another example of when you'd find a peak distribution would be in the heights of individuals in a basketball team. Such individuals are likely to be very similar in how tall they are. In essence, contexts in which you're likely to find very homogeneous individuals or systems lend themselves to having leptokurtic distributions. If the distribution is too flat, such that there is too much variability in the data, then the distribution is said to be platykurtic. Examples of platykurtic distributions are hard to find, but they occur when it's difficult to find a clear mode in the distribution, or when there are extreme scores on both ends of the distributions that's pulling the tails on either end. A final abnormality that can occur in the normal distribution is having the curve be bimodal. This typically happens when you take two normal distributions and put them together in the same data set. Let's say, for example, I had a set of data from which I was only interested in the results from the top half and bottom half of the distribution. I went ahead and pulled the top 10 performing individuals and bottom 10 performing individuals and started running parametric analyses on the data. This is problematic because each distribution is likely to have its own normal curve with its own mode. This variable would have two clear modes and two completely different distributions. By cutting out the middle values, I have created a bimodal distribution that is likely to produce inaccurate results in my statistical analyses. The second way to describe data is through discussing its central tendency or average. The three main types of central tendency are the mean, which is the arithmetic average, the median, which is the centralmost score in the distribution, and the mode, which is the most frequent score in the distribution. Determining these types of central tendency should be a review for you from your earlier stats classes. What's important to note about these measures is that even though our default average is often the mean, there are several situations in which the use of the mean would give us inaccurate results. Let's discuss these. You may recall from our critical thinking lecture on descriptives that when extreme scores are present, the mean provides an inflated estimate of the average. In such situations, it's best to use the median, which takes into account the presence of the extreme score but is not impacted by its extreme value. Another situation in which we would use the median is when we have missing values in our distribution. In such situations, we rely on the median because we're not clear on the size of the missing value. Given that the median accounts for the presence of the value but not the magnitude of the value, it would be the best estimate in such an instance. A third reason for using the median over the mean would be when we're not clear on what the tail ends of the distribution are. For example, a study classifying the frequency of video game usage per week along a scale of 1 hour, 2 hours, 3 hours, and 4 or more hours would be using an open-ended distribution. In such a situation, it would be misleading to calculate the average video game usage using the mean, because we don't know exactly what values are included in the or more category. A fourth reason for using the median over the mean is when we have an ordinal scale of measurement. With such scales, the value of the number indicates the position or rank of the scores, but the difference between the numbers is not interpretable. In such a case, the median is the best estimate of central tendency because it takes into account the ordering of the numbers without being influenced by the magnitude of the numbers. There are also situations in which the use of the mean or median would produce inaccurate results. These situations include when your data is at a nominal level, meaning that the value of the number is only used to name the variable and should be interpreted to represent rankings. We often see this with gender in data sets, in which they are coded as 1 being male and 2 being female. However, these numbers are solely for labeling purposes. It does not mean that a woman is ranked higher than a man because the value of the number is larger. With these kind of data, the mode is the best measure of central tendency to use. Another instance in which we would use the mode as opposed to the median and mean include when we're dealing with data that should represent a whole number. These types of variables are referred to as being discrete. The most common discrete variable that you may run into is the number of people. For example, when discussing the average number of students in different classes, it's best to quote the mode and not the mean, because the mean is likely to give you a decimal figure or fraction that is not interpretable. The final instance in which the mode is more useful to the median and mean is when we want to get a quick approximation of the shape of a distribution. In a normal distribution, typically, and there are exceptions to this, but typically, the mean is equal to the median, which is equal to the mode. Therefore, instead of having to break out a calculator and determine the mean of a distribution, you can quickly scan it. Assuming it's a continuous variable, you can then identify what the most frequent number is and get a better sense of what the mean and median would be just by knowing the mode. The third way to describe data that we'll discuss is its variability, which refers to how spread out the scores are. Note that variability can only be discussed in relation to continuous data, which can only occur with data at the interval and ratio scales of measurement. The most efficient way to get a sense of the spread of scores in a distribution is to compute the range. The range is essentially the lowest score subtracted from the highest score in the distribution. However, one of the problems with using this estimate is that it is heavily influenced by outliers, and it doesn't really take into account which other scores are in the distribution. To get a more accurate estimate of the spread of scores, you can compute the deviation scores. The advantage of these scores over the range is that it gives you information on how much each score in the distribution deviates from the mean. The main disadvantage of deviation scores is that if you summed all the deviation scores up, you would get a sum of 0. To get around this problem, we can square each set of deviations and then sum them. This is referred to as the sum of squares, which I'm sure was discussed quite a bit in your previous statistics classes. In order to account for the total number of scores in the distribution, we can divide the sum of squares by the sample size. This would produce an estimate of the variance. Finally, in order to change the estimate of variability back to the original scale of the values used to compute it, we need to take the square root of the estimate. This is how we end up with standard deviation. The mean and standard deviation form the foundation of several statistical concepts that we'll discuss in this course. If you look at some of the most common inferential statistics discussed in the course, such as correlations and t-tests, you can see that the equations are made up of calculations of the sum of squares, as in the case of correlations, and the mean and standard deviation, as is the case for t-tests. Regression equations are also generated through calculating the sums of squares, sums of products, and standard deviation among the scores in each distribution. Finally, even ANOVA equations rely on the calculation of sums of squares and the mean. It is therefore important that you're able to grasp the concepts in this lecture, as understanding how to compute these basic descriptives will be used to conduct more complex procedures that follow in this course.